I will illustrate the closed interval approach by discussing the following function, which we try to optimize on the interval 0, 6. So we have a cubic function 2x to the power 3 minus 15x squared plus 24x, and I is now the closed interval 0, 6. So we know that f attains maximum, absolute maximum and absolute minimum value. Well, to find those, first we calculate the critical points. So we look on the open interval 0, 6 and try to find the stationary points, because we know that the function is differentiable. So we solve for the zeros of the derivative, and the derivative is given by 6 times x minus 1 times x minus 4. So that's solving for the roots of the quadratic function leads us to conclude that this happens at x equals 1 or x equals 4. So we have two critical points. Now we just compare the function values in 1. So the function value in 1 is 11 and f4 equals minus 16. And we compare them with the boundary value. So we have f0 on the left hand side, so f0 equals 0. And f6 can be seen to be equal to 36. So and now we pick just the maximum minimum value as the absolute minimum and absolute maximum value of f. Yeah, so 36 is the absolute maximum of f, and it is attained at the value 6. And the absolute minimum or the global minimum is minus 16, which is found at the location x equals 4. So here is the general picture. So here we have the graph of the function in blue, sketch at least. In 6 we find the absolute maximum. In 4 we find the absolute minimum. And we have two relative extrema. One is found at the boundary. It's a boundary extremum, which is a relative minimum. Yeah, since if we are close enough to 0, then on this small interval it's the absolute minimum. And we also have a relative maximum. So here are the absolute maximum and absolute minimum, and we have a relative maximum in 1, which is equal to 11. It's not the absolute maximum, since 11 is smaller than 36.